Good. Totally easy, no problems? Yeah. Okay, good. That's where we want to be. Well, I'm sure that that's an exaggeration, but nonetheless. We're going to continue talking about Fourier transforms or Fourier series, and then we'll touch a little bit on Fourier transforms, which is a subtle tweak. But what's the big picture? Like, what are we doing here? Why are we doing these things? Why are we have multivariate this and that and the other and Taylor series and Fourier series? Like, what's the big picture goal?
Because they can be used to approximate complex systems using linear.
Exactly. So we're building a set of toolkits of linear systems that we're going to be able to use to attack much more complicated problems and break things down. And if our solutions look like Taylor series, we'll know what to do with them. If our solutions look like Fourier series, we'll know what to do with them. We'll be able to think about them. So we want to have these tools in place so that we can attack the differential equations with these approaches after the midterm. Okay, so last time we started doing these little averages. What was the average of 1 from minus pi to pi? 1. Exactly. So that one's not hard. So remember, we were using this average notation to be the integral of the function from minus pi to pi divided by the integral not including the function. So, which is just 2 pi for that set. What about sine nx? There's 0. Because this one, if you integrate it, is 1 over n cosine nx, which is 1 over n minus 1 over n. So it always ends up being 0. And what about cosine nx? It was 0 for a different reason, because the integral of this was 1 over n sine of nx, which was actually equal to 0 at both endpoints. But in addition, we should always expect this one and this one to have the same integral because they're just offset by a fraction of the window. Okay, what about this one? It's the same as this, because actually cosine squared plus sine squared is equal to 1. So this is equal to 1 everywhere, right? What about cosine squared nx? This is where we're going to go back to that. This one should be equal to this one because they're just shifted versions of each other. So what about this one and this one and this one?
It's 1/2.
This should be 1/2 sometimes. And what about this one? Also 1/2. Because they're just shifted versions of each other, so they have to take equal parts of this one. But there's an exception for this one. When is it not equal to 1/2 based on the value of n?
N is 0.
If n is 0, then this is equal to 1, and then we're back to the for n greater than 0, and it's 1 for n equal to 0. What's this one for the value of n? It's 0 when n equals 0. So it's the same for n greater than 0. It's equal to 0 for n equals 0. Okay? So there's a couple more that we need, there's one more that we need to think about, or two more that we need to think about, which we haven't talked about yet. What's cosine nx times sine of nx? That's one. And then there's another one. And this is maybe an easier one to do, and it includes this one as part of what it's doing. So let's just think about that one. So that's equal to what? Integral of e to the I mx, e to the I nx dx minus pi, 2 pi divided by 2 pi. Exponentials are easy, right? We just pop them together. So now what's the integral of this? Derivative of e to the whatever is e to the whatever times the derivative of what's inside. So the integral is e to the whatever times 1 over that. Pi minus pi. Okay, things are starting. So this part's not so hard. What's this gonna do? E to the I m plus nx. If it's a, what happened with sines and cosines? This is just a sine or a cosine, right? Sort of, unless something special happens. Does everybody follow me? So I could write this as cosine of m plus n times x plus I times n plus nx. And if m and n are integers, then we said it was 0 in both cases over there. So what is this then? It's going to be 0 if m plus n doesn't do something special. What's the time that m plus n might do something special? If that equals 0, then what happens? Then this becomes e to the 0. What's e to the 0? 1. Then we actually get this integral back again. And we have some problems over here. We shouldn't have even done that because look, now we're dividing by 0. But if we had 0 here, it would have been e to the, it just would have been integral of 1 over integral of 1. And it would have been what? Just 1. 1 if m equals minus n. Okay? Everybody follow how that went? Okay. So what's the cosine nx sine nx one then? Cosine nx sine nx is equal to what? E to the I nx plus e to the minus I nx over 2 times e to the I nx minus e to the minus I nx over 2i, right? So, bing bing, e to the 2i nx over 4i. That's the first one. The inside one, e to the minus I nx, e to the I nx. What's that? This one times this one, what's that equal to?
E to the 2i nx.
Careful, this one's minus and this one's plus.
E to the minus.
E to the I nx minus I nx, or e to the 0, which is just 1. So that's 1 over 4i. And this one is the same. You multiply those two together, you get 1. but it's minus 1 over 4i, because there's a minus sign here and a plus sign here, and then the last one is minus e to the minus 2i and x over 4i. Okay, so if we take our average of this, and our average of this, and our average of this, well, what's this one? 0. Those cancel each other. And these don't cancel because this is a minus 2 and this is a plus 2. So it's actually 1/2 sine of 2 and x. Does everybody see that? Yeah.
How did you get from the first slide to the second one?
Oh, these are the formulas. These are just the Euler formulas for sine and cosine. So, right, we have e to the I theta equals cosine theta plus I sine theta. But I could invert that and solve for e minus I theta equals cosine theta minus I sine theta. So I could solve those two equations for sine and cosine. And this is what they are. Sorry, I thought I had done those before in class. Maybe I haven't.
Maybe you did, I just forgot.
So yeah, these are our Euler formulas. But if I do the plus theta one and the minus theta one, now I have a linear system, and I could actually solve for cosine out of that, and you get this. And I could solve for sine out of that, and I get this. Okay, so I'm just replacing these with the. I could have also just said, well, there is a fancy trigonometric identity that this is equal to that, which is true, but by using the Euler formula, we actually derived it in just 2 lines. So I don't remember any of the trig formulas. I always do it this way. Because this is easier. Or I don't have to remember as much. Maybe it's not easier. I just have to check the algebra. Okay? So now what's the average of this? 0. Because this is a special case of this guy. So this one's also 0. So look at what we've got. We've got any integral of sine is 0. Any integral of cosine is 0. The integral of cosine squared or sine squared might be 1/2 or might be 1. That's important. The integral of cosine times sine, though, 0. And the integral of e to the is only non-zero if they're canceling out. And so it's actually not e to the anything. But any of the other ones with e to the n not equal to minus n, m, whatever, would be 0. So we've actually got a powerful set of things. So now we want to use all these tricks. So this is why Fourier, who was actually a person, even though we forget that it was a person, we think of this idea as being the existence of who he was and forget to even capitalize the F. But Fourier was doing all this stuff to try and solve the heat conduction problem that we're actually going to do afterwards. He was interested in the way that heat spreads and realized all these things tell you something special. If we want to express our function as the sum of, let me write it the right way. If we want to write this thing as the sum, I'm trying to make the notation consistent with what I have in the notes. So we had talked about this right at the beginning. This was our Fourier series. And so there's a constant part, and then there's some sines getting increasingly more wiggly, and then there's cosines getting increasingly more wiggly. And we just said if you had one of these, then we could manipulate it. But what we haven't figured out yet is how you figure out what these are if you have this function. How do I get the A's and B's out of this function? Okay? It's actually not that hard. What if I take the integral, or now I want to do the integral. You don't even have to write the integrals anymore. What if I take the average of f of x times 1? What's the average of this term? Remembering that the average is a linear operator, so I can treat each term here separately. What's the average of this first term times 1? Yeah, it's just that, 1/2 times a naught. And I could actually have written it like this because I know it's a linear operator, and that's just multiplication by a scalar if I wanted to, but this is easy because that's also 1. What's this one times 1? It's going to be a1 times the average of sine. What's the average of sine? 0. This one times the average of sine 2x. What's the average of sine 2x? 0. This one times the average of cosine. 0. This one times the average of cosine 2x. Also 0. So we just use linearity of the averaging to write this down. A0 times 1. So that means that A0 is just equal to the average of fx times 2. Cool. How do we get A1 now? Now we know this term. How do we get that term? Any guesses? It's going to be another average. But I'm not going to put a 1 in there and put something else. But look over there. What can I multiply this by that would single out this term being non-zero and have all the rest of the terms be 0? Sine of x. So if I put sine of x in here, this one would be 0 because it's now an integral, is now an average of sine of x. This one would be sine of 2x times sine of x, which is of this variety, essentially. It's not going to cancel out. So that one would be 0. Cosine x times sine x, that one is this flavor. That's also 0. So all these are 0. 0, 0. Except for this one, which is going to be a1 times what? So it's sine x squared average. What's that going to be? 1/2. So a1 is equal to 2 times f of x times sine x. So I hope you're starting to see the pattern. So let's guess. What's A2 going to be? What's B1 going to be? What's B2 going to be? What's A2? Anybody guess? It'll be a 2. It'll be an average. F of x times something. Sine of 2x. 2 f of x cosine of x. 2 f of x cosine 2x. So you tell me now, tell me which coefficient you want. I just need to calculate one average. Just need to multiply those things together and I get it. So now the Fourier transform, the Fourier series like this is a whole lot more powerful because we actually know how to, just like we knew for the Taylor series, we had to take those funny derivatives and expand them and plug in locally, but we could find all those coefficients. It just took work. Now we have the same machinery for the Fourier transform, for the Fourier series. We can build a Fourier series for any periodic function from minus pi to pi just using these averages. So why is the Fourier series helpful? Why is writing things in this form useful? We talked about it as being an approximation. So in what sense is this an approximation? What if we only keep the first few terms? What is that? What are we talking about if we're only keeping the first few terms of this and not the higher ones? If I have my function x minus pi, it's doing this thing. Whatever. What do I think I get if I only keep the constant part?
0.
Might be 0. It could be offset from 0, but it might have some slightly non-zero value, but it would just be a constant. So it's like a smoother version. What if I do this one plus sine? Does it look like there might be? It does look like there might be sort of a sine wave superimposed. Maybe that you might get a little projection of that. If I did cosine, this little hump right here might select out a little bit of cosine. So on a very smooth basis, I might start fitting this with functions that are getting increasingly more wiggly as I keep more and more terms. And eventually, if I keep all the terms, I should be able to reproduce the whole function exactly. But I'll have to do a lot of work to get there. Does that make sense? Yeah.
How would you know what's the right amount of pairs?
So how do we know with the Taylor series it was the right amount?
Yes. Did we?
Well, we showed that at least when you got closer to the point that we were expanding about, that the errors went down. So what's being optimized here? So is the average value of this function reproduced? It is, because that's this term, right?
Yeah.
We actually have that explicitly written. And then the first little bit of wiggliness is there. What about the derivative of this function? How well is the derivative of this function being reproduced? We know what the derivative of the function is because the derivative is a linear operator. So we can tackle each of these terms independently and take them on one at a time. So the derivative of this is 0. The derivative of this is a minus a1 cosine x. The derivative of this is minus a2 times 2 cosine 2x plus blah, blah, blah. So b1 sine 2 times b2 sine. So how well am I doing at reproducing the derivative? Am I doing as well as I was doing at reproducing the first one? Put it this way. The more wiggly terms, do they have a bigger coefficient than they did before, or they have a smaller coefficient? They have a bigger coefficient. So when I take the derivative, it's getting more wiggly. And what I was removing was the wiggly parts when I was neglecting the higher terms. So I am not doing as well. Every derivative I take, my Fourier truncated Fourier series is less and less accurate. What about integrals? If I went the other way? Leave room. If I do the integral of f of x, dx, I get some new constant, I don't know what. What's 1/2 times pi minus pi? So I have 1/2 a naught times 2 pi. There's the this is the average value. Well, anyway. But I don't want to write, I don't want to evaluate from pi to pi. I want to look at the integral as a point in space. So this one times x plus a1 sine. Sine is going to become cosine of x plus a2 over 2 cosine 2x plus f naught. b1 cosine is going to become minus sine x minus b2 over 2 sine 2x plus that. So now what's happening? How am I doing in expressing the integrals of this function if I truncate my Fourier transform? The more wiggly terms are now being multiplied by what? Smaller and smaller numbers each time. So we threw away the wiggly bits of the original function. If we take a derivative, functions get even more wiggly. So we're actually doing a less good job of expressing higher and higher derivatives. But if we take integrals, the functions are getting smoother and smoother. So in some sense, what we're doing is we're doing a better job at expressing the function and its integrals when we take the Fourier series and truncate. That's potentially, those are the pieces we're describing better. So the smoothest aspects of the function are the things that we're measuring best. There's one more piece in the Fourier transform which is going to be useful later. What's the second derivative of the Fourier transform? So this part is still gone. But what's this one? It's minus a1 times sine x. 2 squared a2 sine 2x. Minus b1 cosine x minus b2 cosine 2x 2 squared. So if I wrote this one as the sum n equals 0 to infinity of, not right that way, a0 plus the sum of n equals 1 to infinity of a n sine of nx plus b n cosine of nx. Right? That's just taking all of them and writing them down that way. What's the second derivative? It's almost exactly the same form, right? I just have a minus sign, and whatever that n is squared up front. And that equals the sum 1 to infinity minus n squared an sine nx plus bn cosine of nx. So I took a derivative and all I had to do was multiply by n squared. So it looks like I'm taking the derivative of this sine nx or cosine nx. It makes taking derivatives and taking integrals really, really easy. The second integral of this function is going to be the same deal with, it's going to be a linear part up front, but the second derivative not not including the linear part, is gonna just be 1 over n squared, 1 minus 1 over n squared times the sum of all the sines and cosines. Does everybody see how that is? So, yeah,
Is the derivative of sine positive or negative cosine?
derivative going this way. Derivative of sine's going up, that's a good positive. But then this one is the negative one. Yeah, so once you've taken two derivatives, it is flipped sign. Whether it flips sign in the first one or the second one is the one that's always hard to remember. This one flips first one, and then doesn't flip in the second one. So by the time you've taken two derivatives, you've gotten.
But it doesn't affect any of our sums.
It doesn't affect this one, yeah. And how do I? What about e to this? What if I write my Fourier transform as like this? Equals C0 plus C1 e to the ix plus C2 e to the 2ix plus C3 e to the 3ix. Is that the same as what I just wrote over here? Could be. What plays the role of 1/2 a0 in this function?
No.
C naught. It's just the same. What plays the role of C1 over here? A1 and B1 together. The B1 part is going to be the real part of C1. And the imaginary part of C1 is going to be equal to A1 almost. There's going to be an I floating around. A1 times I. Everybody see how that works? It's just using the formula that I had written down over here. And the real and imaginary parts of C1 are totally independent. I could make one of them 0, make one of them whatever, so it's just because I'm writing them together in the same term here doesn't mean that I've changed my meaning at all. Can you see that? How do I take the derivative of this guy? That's even faster. This one's 0, this one's the same thing, C1 e to the ix. This one is 2 times C2 e to the ix, 2ix, 3C3 e to the 3ix. So I can take the derivatives really fast now. All I have to do is just pull down the number. Oh, it should be 2i. 3i. And if I do it twice, this is where the minus sign comes from over here. I get a minus sign. Because I got an I the first time I took the derivative, and then I get an I squared the second time. But otherwise the function looks the same. So it's once I've got things written as a Fourier series, it's really easy to take derivatives and integrals. And there's a complex Fourier series and the sines and cosines Fourier series.
Okay. So this is all like assuming that we can write f of x as the sums.
Right, we haven't proved
Is
that.
there like reason for that to be true?
There is a reason for that to be true, which is sort of, you could be very skeptical. You can and should perhaps be very skeptical. Let's see. So how would you go about proving that that was true? So one thing you could do is you could say, I taking a function, tell me how I could be different from that function. Measure a distance away from that function and quantify that difference away from that function on the other side and show that you can't express it. So take function 1, function f and function g, make them just a little bit different in one place, and then show me that the other side responds to those differences. So that if I can't do it, if I can do it for one function, I can clearly do it for a constant. Can I do it for a constant plus a sign? Yes, clearly. Can I do it for a constant plus 2 signs? Clearly. But can I do it for some other weird function that differs from those, say, at one point? And what I would say is that it's in the sense that these integrals measure the distance in some meaningful way, like is the average value different? Is the average value times sine different? Is the average value cosine times different? The fact that we built it this way tells you that you can't ever hide something that this representation can't find, at least in the metric of does its average multiplied by any sine and cosine not equal 0. Sorry, does that make sense? I kind of just said the same thing I showed before.
It does not seem like the average value of a functional versus an interval, like, it seems weird that could tell you anything about the value of that function.
True. So you can try, so let's think of a couple of functions. So if we make a function, it's a constant. We can definitely get it because we actually can get a constant back. But suppose you say, well, I'm going to make it different in one little place, separate from that. Now the average value is going to be a little bit higher because of this difference. And that will eventually get caught by more and more and more of those until we get this one. Then you say, oh no, but I'm going to be even more devious and I'm going to put an opposite sign one over here to cancel the average. So now the average is the same. But one of these products, A whatever, times the function, times the sine of whatever, times x, is actually going to be upward on this part and downward on this part. So the average of that guy is going to single those out. Does that sort of make sense? Cool. And maybe let me put it this way. What if the function I'm trying to express is an odd function? So it goes up on one side of 0 and down symmetrically on the other side of 0. What in the Fourier series is going to be highlighted by that? Can I express an odd function in terms of cosines? No, why not? Because cosine is a even. So for every cosine term, I can't have something that's negative on one side of the axis and positive on the other. But the signs will see it. Or alternatively, if I made an even function in a different color, I couldn't express the even function in terms of a cosine series because in terms of a sine series because it can't see that. But the cosines can. So you could show pretty simply that if I had an even function and I tried to express it with a sine series, I can't do it. Or if I had an odd function and I tried to express it with a cosine series, I can't do it. But the combination of the two means that any function you can come up with, any perturbation, one of those terms is going to highlight it, or a combination of those terms will highlight it. And let's see. There's one strange exception. So one thing we had to do to be able to calculate the Taylor series was we had to be able to take a derivative everywhere. So what does that mean about the function? What can I not take the derivative of? If I drew a function, and I drew it like this, can I make a Taylor series about this point? No, I can't, right? Could I make a Fourier transform of this function? I mean, a Fourier series of this function? I could. It would be hard to get that kink. It's really kind of wiggly. It would probably take a lot of Fourier terms to make that kink sharp, but I could eventually get there. What if I just have a discontinuity in the function? So it's just not defined at that point and down here. I definitely can't make a Taylor series out of it, but can I make a Fourier series out of it? I could try, and I can integrate up to but not including that point, and then I can integrate the rest of the interval, also not including that point. And so I could say, well, if I just skip that point, I can still calculate my integral over my integral, and I'd still be sort of okay. I know that would only be a very minor distance, because only one point gets neglected. So I could do it by writing my integral f of x times whatever sine of x dx in two parts, just the integral from here to here, and then the integral from here to here. And that would only be distant by 1 point's error. And that 1 point is very, very small. So I could say in the integral, it's not going to matter too much that I don't get that point exactly right. Does that make sense to everybody? So what the Fourier transform will do is it'll actually shoot through the midpoint. It'll start to approximate a function that fits, except at that point it'll just fill in a value that you don't have, because all of these functions are all continuous, so you can't make a discontinuous thing out of it, but you can make increasingly accurate continuous approximations to it. If you do this in practice, what it actually does is it starts ringing, just like this. And so it has a lot of trouble making that jump in the Fourier series because it's really, really wiggly to jump from here to there instantaneously. So it has problems. And so it takes a lot of series of the terms in the series, and it eventually makes an approximation going through that point. So if that's true, then you could add any point you wanted that was different, and I could just add that point on, and the Fourier transform would eventually get there. So any little small correction you made to any function you start with, you would be able to build that piece up, because I can build, as long as it's more, well, actually I can't say that. What do I? So, yeah, so you should have to show that these actually can express any function you want. And so what I proposed before was you can take a function and you can take any other function and you can show that you can always tell the difference between them by measuring it, at least in terms of these integrals. So if you take those integrals as the definition of how close you are to matching it, then that's a way of saying that you've always gotten close. But you could have a missing point in your original function or something like that, and then there's no way of doing those integrals exactly at that point, but skipping that point, you can show that you reach it. So the formal statement of what the Fourier series converges to is it converges to any function, even functions which have a countable number of discontinuities. And converging means in the sense that you can break up the integrals and skip those discontinuities. So you do the integral to one side and then the other, and then the other side and then the other. Okay, so we've been messing around with minus pi to pi. How can I change this setup to go from something other than minus pi to pi? if I wanted to go from minus L to L? And I wanted to think about functions that were periodic on this spread. I just need to rescale my axis, right? So I want something like C0 plus C1 I times something when I got to L in X, it would equal pi. So if I had X times pi over L, that does that trick. Does everybody see how that works? C2, 2 pi I X over L. Does that make sense? So I'm just basically rescaling X so that when X equals L, then I would equal pi. So these other coefficients, 2 pi over L, is sometimes written as the wave number or the frequency. And so this is like, if the sine was a wave, this is the wavelength of the wave, and this is 2 pi over the wavelength of the wave is the wave number. So it doesn't matter that I was using minus pi to pi. And in fact, I could make L go really, really far apart. I could make them approach infinity. What happens to K if L goes towards infinity? K goes to 0. On the way there, it's getting really, 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 really small. So if in our original case we had, kind of a big wobble and then smaller wobbles and then smaller wobbles, and the differences between them are integers in units of this wave number. As L gets bigger and bigger and bigger, our ability to measure closer and closer distinctions between neighboring wave numbers gets better. So what this means is, if we're doing Fourier series and Fourier transforms, the longer we listen to the record, the more carefully we can distinguish neighboring frequencies. The resolution, essentially, of our frequency separations goes with the length of the record. And we didn't talk about discrete Fourier transforms, but I could have done this not in continuous integrals, but I could have done it as just sampling along our interval, point, which is what you might do with real measurements. And then we would have had a different constraint on what's the highest frequency we could get out of this. I'll talk about that in a minute. Okay? Cool. We're all squared away for the extent we need to be for today's homework anyway. So next week we're going to talk about vectors, and we're going to review towards the midterm. We're heading towards reviewing towards the midterm, which I think is not next week, but it's the week after is the midterm. We have Wednesday for review and Friday is the midterm. So we'll start the review whenever we get to next week.